Hello everyone and welcome back to the channel. So now we're starting with the second part of electromagnetism. The first part was all about the motor effect, which is the idea encapsulated by the left hand rule. And that was that a current carrying conductor in a magnetic field is going to experience a force. And now we're going to look at the generator effect in the second part of electromagnetism. So let's try to understand what this is all about. So the idea here is that let's say we have this apparatus right in front of us. So we have a magnet, we have a coil, and connected to that coil is a galvanometer, which is basically an ammeter. But just as an ammeter would give us the exact reading of the current flowing, a galvanometer basically just shows us whether current is flowing or not. So for example, if there's no current here, the galvanometer would show no deflection. And if there's some current flowing, it would show us some deflection. So what we'll be doing is with the magnet outside, we'll be carrying out this set of basically experiments, and we'll be noting down what we observe. So the first thing is, if you have your magnet stationary outside, or for that matter, inside the coil, there is no reading on the galvanometer. So in this case, you have no reading on the galvanometer if it's just placed either inside or outside. Now if we have the magnet and if it's moved towards the right, towards the coil, right? So if it's taken like this and if it's moved entirely towards the right, then we do have a reading on the galvanometer. So now what this tells us, combined with the previous experiments results, is that it does not really matter if the magnet is inside or outside the coil, right? Because if it was inside or if it was outside, if it was stationary, it was not giving us any reading. But as soon as I start to move the magnet, or for that matter, I would also see the same thing if I move the coil. So I would get the same result, which is that I would get a reading. So for example, here in this case, what I've done is I've picked up the magnet and moved it towards the coil. So I can say that relative to each other, the magnet and the coil have now become closer to each other. The distance between them has decreased. I could also do the same thing, that if I pick up this coil and move it towards the magnet, it would also have the same effect because the distance between the two of them is reducing. So it's all about relative movement here. So relative movement is something really important when we talk about this. So we are going to emphasize on this a lot. Now, if I pick up the magnet and move it away from the coil, so if I take it towards the left, what I would see is that again there would be a reading on the galvanometer, but it would be the opposite reading compared to what happened in 2. Right? So compared to the previous one, it's going to have the opposite reading. So let's say if I picked up the magnet and moved it towards the coil, so if the galvanometer deflected like this, if I pick it up and move it to the left, then the galvanometer deflects the other way. And again, of the idea of relative movement, it would be the same thing if I picked up the coil and moved it away from the magnet. In both cases, the distance between them is increasing. What else do we observe is that if you have a stronger magnet, or if you move the magnet faster, or if your coil has more turns on it, a greater deflection is observed, right? So these are all ways in which you have a greater deflection, a greater current flowing through the galvanometer. Now, how can we explain all of these observations? That is done using the 2 laws of electromagnetic induction. The first one, Faraday's law, states that the EMF induced across a conductor is directly proportional to the rate of change of magnetic flux linkage, right? So the EMF induced is directly proportional to the rate of change of magnetic flux linkage. Now, what is really the rate of change of magnetic flux linkage? All right, so what is magnetic flux really? So magnetic flux you can just think of as the magnetic field. So the magnetic field is magnetic flux. So magnetic flux linkage means how much of the field is passing through a certain area. But now if we add to the idea the rate of change of magnetic flux linkage, that means that those field lines which are passing through a certain area, how fast are those changing? And the idea you need to remember about this, and you can also write this instead of rate of change of magnetic flux linkage if you want. I often do because I find that that's easier to understand, is the rate at which field lines are cut. I'll be showing you that in the diagram below as well. Factors affecting the EMF induced. So remember that the law itself says EMF induced, not current. Because in the experiment above, what was happening is if an EMF is induced, obviously it's given a closed loop. So when the EMF is given a closed loop, obviously it would lead to the flow of current as well. But the law says EMF induced. So the factors affecting the EMF induced, we've seen all of these above in the changes to the experiment. So you can say the speed with which magnet is moved, right? Because obviously if you move the magnet faster, it makes sense that more field lines would be cut, right? So if the rate at which field lines are cut, if we move it faster, so field lines would be cut more rapidly, that would lead to a greater EMF. Similarly, the magnetic field strength of the magnet, because again, if the magnetic field strength is greater, its field lines are going to be more concentrated, and that would basically lead to a greater EMF induced as well, because more field lines would be cut per unit time. And the third one is the number of turns on the coil. Again, pretty much the same idea. If you have more turns, so when the magnet moves in, it would be cutting more field lines. So the coil cuts through more field lines, that leads to a greater EMF. Okay, so for example, if I look at this here, for example, if these are the field lines, of this magnet, right? So if this magnet is stationary, and this is us understanding how each of those observation works. So for example, there are some points of intersection here, right? So there is some magnetic flux linkage because there are these points in which the coil links up with the field lines, but it's not changing. That's why there was no EMF induced when the coil was either stationary inside or outside the coil. But now when this magnet starts to move, so obviously this point of intersection that you have, it's going to change. These points of intersection are going to change. So we can see that the coil is cutting through the field lines. This is what is going to give rise to an induced EMF. So you can say rate of change of magnetic flux linkage if you want, but with O levels or IGCSE, the examiner also does accept if you say it's proportional to the rate at which field lines are cut. All right. Okay. So that's one law. But that law does not answer why there are different deflections. For example, if I move this towards the coil, or if I move it outside or away from the coil. So why do we have those opposite deflections? That's explained by the second law of electromagnetic induction, which is called Lenz's law. And Lenz's law says this, that the EMF produced is obviously because of some change. Now that EMF produced creates effects which oppose the very change that caused it. All right, it's a lot to break down, so we'll be doing this bit by bit. So the EMF produced creates effects to oppose the change which caused the EMF in the first place. Now, how does that pan out here? So for that, I'll need to turn on the camera. Camera is on now. So let's look at this one. So there's this magnet which has a south pole here, a north pole here, and this is moved in towards this coil, right? Now what Lenz's law says is that obviously there would be an EMF induced in this coil. That's what Faraday's law says. Now what Lenz's law says is that this EMF is going to create effects to oppose the change that caused it. In this case, the change which caused the EMF was this inward movement of the magnet. Lenz's law says that the EMF is going to create a change, is going to create effects to oppose this inward movement of the magnet. So we know that this EMF, when given across a closed loop, it's going to lead to a flow of current, right? And we also know that current, from our previous videos, we know that current produces a magnetic field of its own. So that magnetic field will be in such a way that it's going to oppose the inward movement of the magnet. So to oppose the inward movement of the magnet, this must be repelled by whatever field is created here. Then obviously repulsion is only produced by like poles. So this must be a north pole. And now I can use my trusty old right hand grip rule to figure out how the current must be flowing. So if my thumb is pointing to the left, is pointing to the north, so obviously the current must be flowing in such a direction that it's going backwards through the coil, right? So it must be going like this. So it's going backwards like this through the coil. All right, so questions like these are really commonly asked. So yeah, that's the idea here. So if the magnet is pushed in, the current produces a field to oppose the movement of the magnet. North pole is induced at the left end to repel by creating like poles. The direction of current can then be found using the right hand grip rule. The opposite reasoning for the magnet being pulled out. So in that case, if I'm pulling the magnet away, then what would happen? So if the magnet is pulled out, then obviously an EMF would also be induced according to Faraday's law. But Lenz's law says that this is going to be such that it's going to oppose this movement of the magnet away. So for this to be opposed, it basically doesn't want the magnet to go away. So if this is the north pole, this must then be a south pole in that case. And obviously the direction of current would then be reversed, which now explains why the galvanometer points in two different directions based on whether the magnet is moved towards the coil or away from the coil, right? So that's the idea here. So opposite reasoning for magnet being pulled out, like poles would now be produced by the current to attract the magnet. And Lenz's law is basically just a direct consequence of the conservation of energy. As we are moving the magnet, it has kinetic energy, and that kinetic energy now turns into the energy associated with that current flowing throughout the circuit, which is electrical energy. All right. Another special case of something which is asked in a slightly easier way, but we're looking at the more difficult one right now, just so we understand how this works. So this is a magnet which is dropped above a solenoid and it falls through it, and there's this galvanometer connected, and let's say this is connected to some data logger, so it's connected to some computer, and we're seeing how the voltage produced, the EMF produced, is changing with time. So first of all, I can see that as the magnet is dropped, as it moves towards the coil, what would happen is, again, field lines would be cut. There are field lines here, and as it moves, the field lines would now be here, and then here, and then here. So the points of intersection are changing. We would say that the coil cuts through the field lines. This would generate an EMF according to Faraday's law. This hence causes a current through the galvanometer. There must be a dash pole formed at the top of the coil due to Lenz's law. So if this is a north, it must oppose the downward movement of the coil. So this must then also be a north pole to oppose the movement. But it's not like it's not allowing the magnet to fall through. Yes, it would still fall through, but there would also be some force of repulsion, which is why the magnet falls slower than how it would just under the effect of gravity. Because now, if I think about it, previously there's this force only, if it was just dropped in there. But now there's also this force of repulsion, which is slowing it down. So because the resultant force would decrease, the acceleration that it experiences would also decrease. So it would due to repulsion. As the magnet speeds up, so as it keeps moving towards the coil, it's speeding up because of the acceleration that it has. So as the magnet speeds up, more field lines are cut, leading to a greater induced current and hence a higher reading. What happens inside the coil? So now the magnet is somewhat inside the coil in a position like this. So now what would happen is, obviously, just as there are field lines here, there are also field lines out of the south end. And now those will also continue to interact, will also start interacting with the magnet. So field lines from the south pole are also cut by the coil. And again, according to Lenz's law, if the north pole created one type of EMF, the south pole is going to create an opposite type of EMF. And because, for example, there is a large, let's say that the EMF due to this one is positive, and if the south pole is not as far deep into the coil right now, so it's a small negative EMF. So now both of these are opposing each other, right? Previously we just had the positive EMF due to the north pole, but now the south pole leads to an opposite EMF. So this is going to cause the overall EMF to decrease. And such a scenario will happen that when it's in the middle of the coil, as many field lines are being cut by the coil that are coming out from the north end, an equal amount would be cut by the coil when it's an equal amount of field lines would be cut by the coil coming out of the south end. So both EMFs will be equal. So the overall EMF will be 0. And in the lower half of the coil, again, as it keeps falling down, so now the south pole would be causing, the lines from the south pole would be cut more by the coil, and that would lead to an overall negative EMF. And then this negative EMF would then apply that as it's falling out. So obviously it would be moving faster than as opposed to when the north pole entered, because it's been accelerating the entire way, right? So the max negative EMF would be greater in magnitude than the max positive EMF as the magnet is now moving faster. So as the magnet moves faster. What about leaving the coil now? So when it's leaving the coil, again, it's kind of the reverse of how it was when it was entering the coil. So now the bottom end of the coil, because this is now going to be here. So this is going to be here and this is going to be south. So which end should this coil be? Again, it's going to oppose the movement. So it must be north to attract the magnet and to prevent it from falling. So the bottom end is now going to be a north pole. And obviously as it goes away, the field lines get they get weaker, the spacing increases. So the EMF will gradually decrease and become 0 as less and less, and eventually no field lines are cut. So that's the idea here related to some of the preliminary ideas of the generator effect. Now we'll be starting with Fleming's right-hand rule and the generator in the next video. So see you there.